In the last lecture, I discussed the rule of inferences for propositions. Now, in this lecture, I will discuss the rule of inferences for quantified statements or propositions. Let us refresh the rule of inferences. The general form of rule of inferences are P1, P2. If there is several statements P1, P2, P3, Pn, and all are true, then the Q is the conclusions. This can be represented as mathematically represented as Pn and P2 and dot dot, and Pn implies Q. This is always true, and it is do not require any proof. Rule of inferences are, there are several rule of inferences I discuss: addition, simplifications, conjunctions, modus tollens, hypothetical syllogisms, chaining, and disjunctive syllogism. Rules of inferences for quantified statements. Quantified statements is written as using existential and for all quantifications, for all x, px, then pc if C belongs to the universal set. This is known as universal instantiations. This is known as universal generalizations. This is known as existential instantiation, and this is known as existential generalizations. Rules of inferences for quantified statements. Example: every computer science student is genius. George is a computer science student, therefore George is genius. This can be written as ux. X is computer science student. Gx, it stands for X is genius. The following steps are used in this argument. Step 1, for all x, ux implies gx. This is a hypothesis since it is given. That means every computer science student is genius. This is a hypothesis. Now George is a computer science student. This is instantiations. It is a universal instantiation using step 1. And then U George means George is a computer science student. Now the conclusion is G George means George is a genius using modus ponens. Now modus ponens is from 2 and 3. This is true and this is also true. The conclusion is George is a genius student. Another example, so that the premises student, there are premises a student in the class not read the book, and everyone in this class passed the first exam implies the conclusion someone who passed the first exam has not read the book. Now it can be written, it can be formulated as let xex be x is in the class, px be x has read the book, and px be x passed the examination. Then the premises are for all there exists x cx and not px. Why it is written as a student in the class has not read the book. Now cx stand for x is in the class and not bx. Bx means x has read the book. So not read the book means not, this is not operator, not bx, and both statement should be true simultaneously. Hence here is AND operator is used. This is the first premise. A student in the class not read the book. This is the first premise. And second premise is everyone in the class passed the first exam. Now Px means x passed the first exam. Cx means x is in the class. So Cx implies Px. That means everyone. That means x passed. X is a student in the class and he passed the exam. And everyone means for all. Therefore, for all x, Cx implies Px. So the conclusion is there exists x, Px, and Bx. That means someone who passed the first exam has not read the book. Now it is derived using a sequence of steps. The steps are as follows: Cx and not Bx. There exists an x such that Cx and not Bx. This value is true. This is a premise. Similarly, Ca and not Pa. This is an existential instantiation from 1. The instantiation means we can use a constant or any values for the variable. Here A is a value for the x. Ca means simplifications from 2. Simplifications from 2 means Ca and not Pa. That means both should be true. That means Ca is true. For all x, Cx implies Px. That is a premises. It is given. Similarly, it is instantiated with a value A. Ca implies Pa. And using modus ponens from 3 and 5, we get Pa. Now, not Ba means simplifications from 2. Since this is and operator, hence both are true. Hence not Pa is also true. Now Pa and Ba both are true. Pa and Pa are both are true. Conjunctions from 6 and 7. 6 and 7. It make when we convert it into the variable A into variable and using quantifications, there exists an x such that Px and Bx, which clears our the statement, which is the solution of which is the conclusion of the given problem. Anyone perform well is either intelligent or good actors. If someone is intelligent, then she can count from 1 to 10. Gary performs well. Gary can only count 1 to 3. Therefore, not everyone is both intelligent and good actor. Now it can be formulated as Px, x perform well. Ix means x is intelligent. Ax means x is good actor. Cx, x can count from 1 to 10. Now hypothesis. Anyone performs well is either intelligent or good actor. How we can write it? The hypothesis can be written as Px for all x, Px implies Ix, that is intelligent, and Ax, that is in actors. That means Px, person X, as either intelligent or a good actor. This is OR operator. Next, if someone is intelligent, then she can count 1 to 10. It can be written as this: for all x, Ix implies Cx. Gary performs well. Gary performs well means Pg. This is a instantiation of the statement Px. Gary can count only from 1 to 3. That is, he cannot count from 1 to 10. So here not operator is used. Conclusion: not everyone is both intelligent and good actor. That is, it is a conclusion for all x, ix and ax. That is, not everyone is both intelligent and both value is not true. So it is ANDed. Now, how we reach the conclusion? Hypothesis. First is one is hypothesis. Second one is instantiations. Second step. Third step is also an hypothesis. Fourth step, the modus ponens using 2 and 3. This is 2 and 3. This is modus, using modus ponens we get this statement. Fifth one is a hypothesis. It is given. This is the instantiations of fifth step. Ig implies Cg. Not Cg is a hypothesis. Not Ig is a modus steps 6 and 7. Modus tollens steps 6 using 6 and 7. And this is additions. We get a not Cg and not Ig. We get another statement, not Ig or not Ag. This is also true. Equivalence of step 9. We make an equivalence statement using De Morgan's law. The 9 and 10 are equivalent. Now this can be written as, for there exists an x, not ix and ax. That means there exists an person such that both they are he is not intelligent and actors, good actor. This is our conclusions. That means a person cannot be both good actors and intelligent. Now this is we changes using an existential quantifier to for all by, as you know that existential quantifiers is negate of for all operators. Hence we reach our conclusions for all x, that is not everyone is both intelligent and a good actor. In this lecture, we say the rule of inference, how how the conclusion is created, constructed, and how we apply the rule of inferences for nested quantifications, and how we prove some statements using the hypothesis and the rules. Thank you.